Assalamu alaikum, dear students. In today's video lesson, we're going to start with chapter number 2. And I can tell you that this chapter, it is the second most important chapter in grade 12's physics. So make sure you continue watching these series of video lessons because I'll be giving you some keys and study tips. Inshallah, it will make it very easy to understand chapter 2. Okay, now what are we going to study with chapter number 2? The first thing we're going to study to start learning, let's say, is torque, and then after that we'll learn about rotation and inertia, and then after that we'll learn about rotational dynamic as well. Now the first thing that we have is torque. Now let's see what is torque, how we can calculate torque, and everything else that is related to torque. Now, but before that, let me just take you back to grade 11 for a second. In grade 11, we said, what happens if we have an object that is on a surface? If you apply a force on the object, this object, of course, we're traveling, let's say, a certain distance here. So that object was traveling a certain distance, and that is very obvious, of course. Then once you were doing this, you were doing a certain amount of work, and you were spending some energy here. This here, okay, imagine we're going to do almost like a similar thing here. So let's say we have a force, but this force is applying or acting at a certain distance on an object, let's say, or a certain distance to the axis of rotation of an object here. So once we do this, now instead of this force making the object go forward or backward, it is going to rotate the object. Now that effect of rotation, or that cause in here, what you see, it is this effect of the force, you can call it a torque. So this is what is called a torque in here. And torque, of course, it is, or we use a symbol for that. This symbol you can say, or it is a Greek letter, all right? Its name is tau, but we'll never use tau. We'll just call it torque, and that's it. So that is clearly what a torque is. So if you want to define a torque, we'll say it is a quantity that measures the ability of a force to rotate on an object about some axis of rotation. I'll repeat. You can say it is a quantity that measures the ability of a force to rotate on an object, which is clearly at some, let's say, certain distance to the axis of rotation. So that is what we have as a torque. So as an equation here, we can say torque, all right, it is equal to force times distance sine theta here. So what is exactly torque, all right? Depends on, this is clearly the equation. It depends, we can say torque, it is equal to force times distance times sine theta here. So now you can see that torque is directly proportional to the force, okay? So you could also say the things that the torque depends on are this three thing here. And also we could say the torque is also directly proportional to the distance. And of course, torque is also depends on the angle as well, as long as you could say between 0 to 90, or you could say 270, let's say 180 to 270. But we're not going to use this one here, by the way, this part, so you could just erase this one. As long as you can see it is, the torque is directly proportional to the angle if it is between 0 to 90 at this point here. So what do we call each one of these parts? That is clearly the force. Okay, and this is the distance here, but at this point we call it the lever arm here at this point. So what is the lever arm? Watch this. Imagine that is the force where the force is acting. This is perpendicular distance. It is what is called the lever arm here. Okay, but what if, let's say, if the force is not acting, let's say, and you can see that the angle between the force and the distance is 90. But what if the force is not 90? Let's say, take a look at this example. We have this example, which is from the book. By the way, we're not going to focus on this one a lot because we have other methods, but just in case, yani, let's say here is a force is acting on this spanner, you could say. Here is a force, and this is the distance, but this, you can see that this force is acting at some angle to the spanner. So, and we said that this lever arm, it is a perpendicular distance here. Or you could say the lever arm, it is the perpendicular distance between what? Between the force and the axis of rotation, this perpendicular distance. Once again, what if the distance is not perpendicular? Then this is what we use. That is, by the way, I'll repeat this. We only do this because this is one of the diagrams of the book, you could say. Otherwise, we don't use this. We have other methods to use in here. So you can see that if I do this, this would be the you could say right angle, that is where the force is acting. So this side here, these two are, of course, same angles here. So this is going to be opposite of this angle. So this side, it is what is called d sine theta. And now you can call this d sine theta the lever arm at this point here, the lever arm, which you can see that it is the perpendicular distance between the axis of rotation and the force at this point. But like I said, we're not going to do this, so don't worry about this. Just remember, in Wizard, if they brought this one, for example, they might give some letters. We'll add some letters to these, for example, here, A, B, for example. Let's just say C, and maybe a point here, let's say D. They might say which one of these points represent the lever arm, and in that case, you just have to choose C, because this perpendicular distance, it is what is called the lever arm. So what do we do instead of this? Okay, so just be patient. We'll cover the whole thing here. But first of all, let me tell you one more thing. Okay, now regarding the torque, let me write the equation again. It is equal to force times distance sine theta. By the way, if the force is acting at a right angle here, what is the angle is going to be 90, yes? If the angle is 90, you really don't have to write sine theta, because we know that sine 90, it is equal to what? It is equal to 1. So you don't have to write this one. In that case, you could just write F, or force times the distance. So we only write the sine theta, let's say, if the force is acting at some angle to the, let's say, to the distance, which is clearly at some, where you can see that there is a certain distance from the axis of rotation. Now, so you could see that the force or the torque depends on each one of these two here. Remember this. And then regarding the unit of the torque, what does it depend on? Now, we know that the unit of a force is measured in Newton. The unit of a distance, it is measured in meters. So we can say torque, it is measured in Newton meter here. So this is the SI unit, you could say, of the torque here. That is the international unit of the torque. Now, there is more actually. What if I want to, for example, break down these units into simpler or basic unit? What will I get? We know that Newton is a unit of force, and force that is equal to mass times acceleration, right? The unit for mass is kilogram. The unit for acceleration, it is meter per second squared. And then if we bring this meter back in here, so that is what we get as a result of this. So what is going to be the final answer for this? We can say kilogram, meter times meter. That is going to be meter squared divided by second squared. So we can say this is also a unit of, or you can say an equivalent unit for torque. You can call this one the basic, or the base unit of Newton meter here, but Newton meter, it is the SI unit. So in calculations, we'll always use Newton meter, but if you ever see, for example, in Wizari, because once this one has been in Wizari once, it says which one of these is the base unit or equivalent to the unit of torque. So of course, in that case, you can choose this one here. Now, one more thing regarding the torque is this. Remember, torque is a vector quantity. And what do we mean by a vector quantity here? Okay, imagine this. Let's say we have a seesaw, and if you apply a force, let's say at this side here, this force is going to rotate the seesaw in this direction, right? Once again, if you're not sure, you could always draw a clock at this point here, 12, 3, 6, and 9. If something rotates clockwise, previously we've learned that we assigned negative to that let's say, direction. And then if something, what if you apply a force at this side here, then this force is trying to rotate the seesaw in the opposite direction here, or you can say opposite to a clock, which we call it counterclockwise. In that case, the torque is going to be positive. The torque at this side is going to be negative. So torque is a vector. It has both magnitude and direction. Regarding the magnitude, you will use the equation F times distance sine theta. That is how you can find the magnitude. Regarding the direction, you have to know which way it is rotating. And I'll tell you more about how we can tell which way it is rotating. But for now, just remember, if the rotation is clockwise, the same as a clock, we call it clockwise rotation. And if it is opposite to a clock rotation, we call it counterclockwise rotation, and it's going to be positive here. Okay. Now, regarding the direction, perhaps maybe I could tell you right at this point, always make sure that you have a pen in your hand or pencil, and then place one end of the pen or pencil right on the axis of rotation. Make sure you don't let that end go, all right? Just make sure you don't do that, all right? And then after that, you apply force exactly at the same point where the force is acting. So at this point, the force is acting downward. So if you do this one here, you can see that this thing is rotating clockwise. What if you do the other side, of course? Once again, always place one end of the pen right on the axis of rotation. Don't forget. That is the place where you put your pen or pencil there. And then you don't ever let that side, for example, slip beneath your finger or whatever. Then this force here, it is acting this way. So if you apply force downward here, you can see that this one is going to make it rotate counterclockwise, which is going to be positive. Okay, now, the next thing, perhaps I'll give you some examples, but there is one more thing. What if we have more torques acting on an object? Then clearly we can find the net torque. Okay, so maybe perhaps let's just take a few examples first. All right, let's say find, right, the both magnitude, let's say. Find both magnitude and direction of the torque, or let's say of the net torque here. All right, so we have, let's just use some examples here. Let's say here we have an object. This is the axis of rotation, and here's the forces acting at this side. Let's say the size of this force is 100 Newton. It is acting at a distance of, these are not to scale by the way, 3 meters here. So how do you find the torque in here? Because this force is acting at right angle 90 degrees, so at this point we don't have to write any angles here. So you could say torque, you could write it whatever you want to here. I would prefer, I don't know, this way. So torque it is equal to force times distance. Once again, we don't need the sine theta. So the force is 100 Newton, the distance is 3, so it is just going to be what, 300 Newton meter. That is the direction, you could say the unit. What about the direction? Don't forget that, right? I would recommend you actually writing from the start so that you don't forget at the end. So once again, place one end of the pen at, let's say, the point where the axis of rotation, which is at this point here. That is where the thing is going to rotate. So if you apply force in this direction, it is going to rotate. It is going to rotate downward, yes? And because it is rotating downward, that means this is clockwise. So you can put a negative at each one of these cases right here. Now, what if, let's do more examples maybe. Okay, so we can say negative. If you don't want to write negative, you can also write 300 Newton meter. Instead of writing negative, you can call it clockwise. Right, but try not to write negative and clockwise together, because that would be basically this one. It would be the reverse of, if you write negative clockwise, that is almost like the reverse of clockwise, which is going to be positive here. Okay. Let's say one more example. What if the force is acting at some angle here? Here's, let's say the force is acting at this point at some angle 30 here, and this is the axis of rotation. Once again, the distance is 3 meters here. And the force is still 100 Newton. Okay, so how do you find the torque at this point? We can say torque, it is equal to, this time force times distance, because we have angles, we can say sine theta. Right? Remember the other diagram, I told you not to worry about this. So that is what we're going to do. At this point, the force is 100, okay? The distance is 3 times sine of the angle. That's the whole thing you need to know, which is clearly 30 here. But now, regarding this one here, let me write 30. Okay, sine 30 is half, you could say, so that is going to be 150 Newton meter. But this time, is it clockwise or counter? Once again, place the pen the axis of rotation, and then apply, you could use another pen to apply the same force, even in the same direction. Once you do this, for example, you can see that it is moving or going to rotate this way here, so this way is going to be counterclockwise. I'll repeat this, all right? So once again, you do this one here. If you apply a force there, you could see that it is going to rotate the pen in this direction here, which is clearly counterclockwise. So you can write positive, or you can just leave the positive, you could say counterclockwise. Right, remember C4, counterclockwise. All right, now regarding this one, what if the angle is given at a different case or a different situation here? Right, what if the angle were given here? Okay, So the same example, here's the axis of rotation. Here's the forces acting, 300, you could say 100 Newton. Okay, this time here, let's just say, what if the angle is given with a vertical? Here's 30 degrees, you could say, or let's just make it, I don't know, maybe 60 degrees. These are not to scale, the distance is still 3. Okay, so how do you, or what do you do this? How do you find the torque of, or the torque for this question here? So once again, we'll say the torque is equal to force times distance, once again, sine theta. So the force is 100, the distance is 3. Now, remember this, at any point, don't forget this. At any point, if you ever want to, for example, or if the angle is given that is not with the distance, just make sure that the angle must always be attached with the distance or between the force and the distance. So what do I mean by this? You know that this is where the force is acting and this is the distance, right? Is this angle between the force and the distance? No, this angle is between the force and the distance. So you can write the note here for yourself, all right? You could say the angle theta must, right, always what? Be, or let's say must be between the force and the distance. The force and the distance, you could say. The force and the distance. In other words, you can say it must be attached with what? With the distance. With the distance. Well, what if it is not with the distance? Then you clearly know that this angle, so is this one now, let's just go back to the note here. Is this angle between the force and the distance? No, because that is the normal, you could say. So this is the force and this is the distance. So this angle here, it is what is between the force and the distance here. And even if it is at this end, you can extend the distance just for yourself, just to make sure that is between this and that. We know that if this angle is 60, how do I find this one here? You do know that this angle, it is 90 degrees, right? So if this is 60, what is this angle? That is clearly 30 degrees, because 90 minus 60, how else would you find that? 90 minus 60, that is going to be 30. So this angle is 30 degrees. Once you've done this, so just sine 30 and that's it. So once again, you get 150 Newton meter. For the direction, once again, it's going to be same way as it is. So it is counterclockwise. So you could say positive, or you could write 150 clockwise, counterclockwise. Okay, here's what you can write, and that's it. That's the whole thing you need to know. It's super easy if you don't get yourself confused. Now, there's one more thing. What if we have, let's say, more than one torque? Let's say we have another case here where we have, let's say, here's the axis of rotation. A force of 100 Newton is acting at a distance of, let's say, at a distance of 3 meters. And then there is another force acting at this point here. This force is 20 Newton, acts at a distance of, let's say, 1.5 meters. And then there is a force here, which is, let's say, of 50 Newton, acts at a distance of 2 meters. These numbers are just for the sake of example. Okay, so how do you find, let's say, we have something called the net torque. When we have more than one torques, we can find the net torque, the resultant, all right? How do you find the resultant? You can say torque 1 plus torque 2 plus torque 3 and plus, let's say, plus torque 3 plus any torque that you have, for example, let's say. But once again, if there is a torque that is counterclockwise, that is positive. If it is clockwise, it's going to be negative. So you can put that in a bracket, then you can subtract, and that is what we have. So can we do this one here? First of all, let's start with this force in here. So we have 50. Okay, so let's just call this one F1 and call this one F2 and call this one F3. So the torque of F1, you could say it is F1 times D1, you could say. You can call these one D1T here. So F1 at this point, it is 50 times the distance is 2, so it is going to be 100. Is it clockwise or counterclockwise? So if you do this, a force applied downwards, so it is going to be counterclockwise, which is positive. That is the first one. What about the, let's say the second one here? Let's say torque 2. Is it clockwise or counterclockwise if I start from the direction first? So it is going to move this way, which is clearly clockwise, you could say, or negative. Negative F times distance. You can see the angle is not given, so you don't have to write sine theta. So the force that we have, it is negative 20 times the distance is 1.5. So 20 times 1.5 is going to be negative 30 Newton meter. This is also Newton meter, by the way. Okay, that is torque 2. What about torque 3, let's say? We're going to use the same thing here. Torque 3, it is equal to F3 times D3, you could say. This is F2, D2, doesn't matter here. All right, so the F3, it is 100 Newton. By the way, clockwise or counterclockwise, this is also clockwise. Always place one end on the axis of rotation. I don't want to do that because it might, when the smart screen would respond to this. But once you do this, so if you rotate downward, you can see that it is going to rotate clockwise, which is negative. So negative 100 times the distance, watch this. The distance always between where the force is acting all the way to the axis of rotation, which is 3 meters. Make sure you don't just do, for example, or measure this distance. No, it is always between where the force is acting, that is this point, all the way to the axis of rotation. The same thing with F2, which we did. So in this case, it is multiplied by 3 meters here. It's going to be negative 300 Newton meter. Now, so this point here, I have 3 torques. How do I find the net or the resultant here? You could say the net torque here, that is equal to torque 1, you could say, plus torque 2 here, plus torque 3. I've just noticed that every time I'll write the symbol of torque in a different way, but well, it makes no difference. All right, so at this point, torque 1, we said it was positive. What was the value? It was 100. Plus torque 2 was negative, and it is negative 30, right? Negative 30 plus torque 3 is also negative, which is 300. So now we can say 100 plus minus 330, right? So now the final result is going to be negative 230 Newton meter. You can see that it's negative. You can also write 230 Newton meter clockwise, if you don't want to write the negative at the end here. So this is how you can find more than one torque if it is given. So you would just find the resultant by adding all the torques together. All right. Now let's get back to the main page. Remember, torque, we said, it is a quantity that measures the ability of a force to rotate an object around some axis of rotation. Torque, we also said that it is a vector quantity. It is measured in Newton meter. We said if the rotation is clockwise, the torque is negative. If it is counterclockwise, it is positive. What about the lever arm? Remember, we said the lever arm, or d sine theta, it is the perpendicular distance from the axis of rotation, which is drawn to the line where the force is acting. Don't forget that. Okay, here's the equation for torque, and these are each of the letters that we have. Just remember this. This diagram is basically Book's diagram. This perpendicular distance, it is what is called d sine theta, or the lever arm here. But in calculations, we'll just use, for example, the regular distance. But then, of course, we'll take this theta, which is between the distance and the force, which gives us the same effect or the same thing here. We also said that, for example, Newton meter is the unit for a torque, but it is equivalent, it is equal to kilogram meter squared over second squared, and that is where it comes from, you could say that. So if they ever, for example, ask you what does the torque depends on, you can always write the equation, yeah? So here we know that torque depends on what? Or it is equal to Fd times sine theta, or Fd sine theta. So it depends on the force, which is directly proportional, depends on the distance directly proportional, and also depends on the angle which the force is acting here. All right, what do we do if we have, these are regarding the direction of the torque. We said if it is counterclockwise, it is positive. If it is clockwise, it is negative. If we have more than one torque, then we just add them to find the net or the total here. The angle theta, all right, remember this note, the one that I wrote for you. This angle theta must always be between the force and the lever arm, or it is extension. What do I mean by it is extension? Let's say if we have a lever, a beam or something. If the force is acting right at this point here, you can see that this is the end of the distance here. So at this point, you could extend the distance just a little bit so that you can see what is this angle here. But of course, this is the distance where you calculate where you use to calculate the distance. You don't use this extra distance here. Okay. Now we have a study tip which is also important. We get this one from the equation. It says the further away from the axis of rotation, right, the bigger the torque, which means that the easier it is to rotate here. Isn't that obvious here? We know that torque is equal to force times distance sine theta. Now if I give you, let's say, an example for this here. Let's say here's a beam, and this is the axis of rotation. We can apply this force here that is 100 meters, let's say, at different locations. Let's say we could do that at a certain distance here. Location A, for example. See if we can move this one here. What if I, for example, apply or use this force? All right. What if we, for example, apply or move this force at a further distance here? Let's just say we move it here. You can see that the distance gets larger. So the larger the distance based on this equation, because these two are directly proportional, so the larger the torque would be, which in other words, you can say the easier it rotates. What if you move even to a further distance? So you can see that the further the distance, the bigger the torque will be, which means that the easier the rotation occurs. And that is, I think it's common sense. You can see that too. Okay, now going back to this diagram here, or this table is also one of the things you need to know. When do we get maximum torque? If we have, remember this, if we're going to do the following here, you must have a certain force and a certain distance here. Let's say we have a lever arm. There is a certain force, let's say 100, and a certain distance, let's say 3 meters. So when do I get maximum torque for this force and distance? We'll get maximum if the angle between the two is 90, you could say, or the other side, doesn't matter here. So force times distance, if the angle is 90, then I'll get maximum torque for this term. When do I get half of maximum? Half of maximum torque for this one here. Of course, if the angle now, let's say here's the same case here, but if the angle is 30 this time, with the same force and distance, right, then I'll get half of the previous one. If I do this, the calculation here, I'll get 300 Newton meter. Remember, that is clockwise negative here. I've just, let's just make it positive. So in order, we don't have to go through this one here. Let's just make this one upward. Okay, if that is the case, it will be positive here. What about, this is the same force and distance here, but if we change the angle, make it 30, all right, so that is going to be 100 times the distance, which is 3, times sine 30, which is half in this case, we'll get 150. So you can see 150, it is half of 300. But remember, for the same force and the distance, okay? So we'll say that at 90, we get maximum torque. At angle 30, we get half of maximum. And by the way, instead of 90, you could use 270, which is exactly at the other side here. Makes no difference here. This, for 30, you could use 150. Sine 150 and sine 30 basically gives you the same result here. But then there's another important part. When do we get minimum or zero torque? Now let me tell you regarding this. So we'll get minimum or zero torque if, watch this one here. There are some cases that you really have to be aware of this, and you can write some notes here. Let's say this is the axis of rotation. Okay, let me just write it here. Axis of rotation. Remember this, if the force is acting on the axis of rotation, no matter which direction it is, okay? At any of these points here, even if, for example, the force is acting at some angle here, let's say whatever the angle is, if it is acting or passing through the axis of rotation, then we'll say the torque of each one of these is going to be 0. So make sure you write this one down. If the force is acting on the axis of rotation, there is no turning effect. There is no torque. Okay, so the torque immediately will be 0. It is as if, for example, imagine if you have a beam, let's say this pen. If you apply force at any of these points, it's going to rotate. But imagine if you apply force right at this end, or let's say here, or at any other point here, for example, that would be pushing the whole thing. So there is no rotation here. Okay, so there will be only rotation if the force is acting at a certain distance to the axis of rotation. So why is the torque is 0? You could, one of the reasons you could say because there is no distance for the force, that is one. Okay, that is Or you could just say the force is acting on the axis of rotation, and that's it. Now, there's one more thing here. So this force clearly causes a nice torque or causes a rotation. What if the force is at this point, let's say? Watch this one here. What if this force is acting at this point? So what do you think will happen? So once again, you might not see this one here. You might say, here's a distance and here's force, so this one produces a torque. That is also does not produce any torque. Why? For two reasons. One of the reasons you could say, okay, let's just erase those here. Now watch this. If I extend this force here, now can you see that whereas this force is passing through? So isn't it passing through the axis of rotation? That is also, we said that any force is causing, or let's say acting on the axis of rotation, it is zero. So once again, this force is not acting on the axis of rotation, but you can see that. You could see this line, and we call this line extension, right? So we'll say either if the force is acting on the axis of rotation, or if it is extension is passing through the axis of rotation, there will be no torque at all. So this force produces no torque. Once again, the reason why, because there is no distance between the force and the axis of rotation. That is not a distance here. There is also another way you could say, because both force and distance are parallel, that is also true. You could say that. But the easiest thing you can say, because the force is acting on the axis of rotation, or the extension of the force is passing through the axis of rotation. In these cases, we have no torque. And that happens, of course, when the angle is, let's say, 0 or 180. So these two cases, the force is causing no rotation here. We have a question here, says, in which of the following angles, or in the angles in the bracket, the torque is maximum? Okay, in which one of these cases the torque is the greatest, let's say, in which one of these angles? We said at angle 90, the torque is maximum, right? Okay, and then which one is half of maximum? That is going to be 30. Which one of them is going to be 0 or no torque? It is 0 and 180. These two angles, there is no torque at all. Okay, we have another, these questions, I've almost went through these or gave you examples for this, but there is one more which I would like to perhaps explain a little. Okay, it says, what does it say? Find the magnitude and the direction of the torque here. So you can see that this is the torque here. It is equal to force times the distance. The force is 100, the distance is 3, so that is 300, you could say. Once again, is it clockwise or counterclockwise? You use your pen and place one end to the axis of rotation and then just rotate it. You'll see that it is going to make it rotate counterclockwise, which is positive. What about this one here? Watch this. We have an angle here, so no angle there, or you could say perpendicular, so we don't write the angle. But here, the torque is equal to force times distance sine theta. Remember the angle? We said the angle must always be attached with the distance, where it's basically between the force and the distance. Okay, so at this point here, you could see that the force is 90 times 4, and then sine this. Is this 40? This is the distance, and this is the axis of rotation. Is this distance or this angle between the force and the distance? Yes. Is it attached to the distance? Yes. So you'll just say sine 40, and that's it. So you could just find the magnitude of this, which is going to be 231. 231. But which way is it rotating? Once again, watch this. Always place a pen, and here's where the force is acting. So you could just do this one here. So once you do this, you can see that how it is rotating, which is clockwise. So you could write a negative at this point right here. Now, the third one here, because we have more than one force, so we're just going to do this question again. I mean, we've done the other one, but I would like to do this one so that you fully understand this one here. Okay, so let's do this one. What does the question say? It says, what is the total or the net torque around O? So clearly, point O is the axis of rotation. But before that, remember the note, it says what? Always use the angle between the force and the distance, or it is extension here. Okay, so what do we have now? As you can see, there is one of the forces that we have, F1, but it is at an angle 30. This angle 30, is it with the distance now? So remember this. And then we have, there is another force here, which is 200 Newton, but watch this. right? We have two distances. One of them is 2, the other one is 5. Which one, not 5, my bad. Let's just move this one, it is 1.5. Which one are you going to use, or are you going to use both of them here? So I need you to pay attention to this detail as well. Okay, so let's start with perhaps maybe reconstructing a similar diagram at this point here. So let's say this is what we have. This is the axis of rotation. So let's start with the first one here. That's what we have. Here's the other one. Okay. Here's this angle that we have, which is 30. This force is 450. This distance, it is 1.5, as you can see here. That is where the force is acting all the way to the axis of rotation here. So once again, torque it is equal to force times distance, and because we have angle, sine theta. What is the force over there? It is 450. Let's just leave a space here. 450, right, times, what is the distance? 1.5. What about the angle? Sine the angle. Once again, is this angle between the distance and the force? The answer is no. This is the angle that is between the force and the distance. So we know that this angle, this one right here, it is 90, yes? If this is 30, what is this angle? Clearly 60. Or you could just say 90 minus 30, that would be 60. Okay, so sine 60. Now, regarding the direction, which way is it rotating? Which way is it rotating? You can see that it is pointing downward. So if you point downward here, that is going to rotate clockwise. So you can add a negative here. So what is the magnitude of this force? It is going to be, it is 200 Newton, you could say, right? No, wait. The torque is, what is the magnitude of this torque? You could use a calculator. It is negative 584.6. That is the, you could say, the first torque, or the torque for the first force, you can say. What about the second torque? So we can say torque 2, force times distance. We don't have any angles for the second one, so we don't write that. But I need you to be careful regarding the distance here. What is the force? The force is 200 times the distance. Now, what is the distance? By the way, do I have to use this 1.5? No, because that is not where the force is acting. What do I need to use at this point? Watch this. We said always remember where the force is acting all the way to the axis of rotation. So the distance is going to be, is it just 2, let's say, or 1.5? No, it is the whole distance, which is going to be 2 plus 1.5. That is a total distance of 3.5 meters in here. Regarding the direction, is it going to be clockwise or counterclockwise? As you can see here, it is pointing upward, which is going to be counterclockwise. I mean, if the force is pointing upward, and if you place this one here, you would see that this would rotate the pen upward here, which is going to be counterclockwise, which is positive. Now, we could see that here, 2 times 3.5, or 200 times 3.5, it is going to be 700 Newton meter. 700 Newton meter. That is clearly the torque that is produced by F2. Now, regarding the total, how do you find the total at this point? Well, we can say regarding the total, that is equal to just the total or the net torque, it is equal to torque 1 plus torque 2, we could say, plus torque 2. Okay, now what is torque 1? We said that is negative 580. It is negative 584.6 plus the second one, which is 700. Clearly 700 is bigger, so the net is going to be, what is it equal to? It is equal to 115.4. 115.4 Newton meter. Once again positive, which means that this beam is going to rotate counterclockwise eventually. All right, now that is regarding this one here. Okay, now moving to another question. What does it say? Explain, that is chapter review question number 1, says explain how an orthodontist uses torque to straighten or reline teeth. Now, imagine, look at these, for example. Here's one of the teeth, especially for those who, for example, use or add braces to their teeth, let's just say, just to straighten or reline them here. So that is basically what happens here. let's say this is one of the teeth that there is, then they'll add the brace right at this point. Let's say if the teeth is either out of the line, let's say, or out of the line, let's say outward, or could be inward, right? So they'll add a brace. Then the base of the tooth clearly serves as the axis of rotation. So when you apply a force at a certain distance clearly, so the length of the tooth would be the distance between the force and the axis of rotation. So this force, if it is, let's just say if it is out of the line here, they'll just push back using the braces, push back the tooth so that it goes back to the line. What if it is outward? They'll just pull the tooth, for example, back to the line. This is how it straighten or realign. So we can say orthodontist use a force at a perpendicular distance to the tooth, which causes the tooth to rotate so that it can realign, while the base of the tooth serves as the axis of rotation. Okay, so orthodontists use braces to apply force at a distance from the base of the teeth, which is serves as the axis of rotation. This question is one of the important questions that we have, and I need you to pay attention to this one too. What does it say? It says, which of the forces acting on the rod in figure 2.15 will produce a torque about the axis at the left of the rod here? So here's the axis of rotation. We've mentioned earlier that if a force is, by the way, there was a similar Wizati question to this one too, but there is also another force in there as well. We said if a force is acting on the axis of rotation, that force produces no torque. All right. What about the other forces, for example? If this one here, the force itself is not acting, but if you extend this force here, you can see that this one is also passing through the axis of rotation. So we can say the extension of this force is passing. So this one producing no torque as well. Only F2 is producing a torque around this axis of rotation. Okay, so once again, F1 produces no torque. The lever arm is 0, you could say, or the extension of the torque is passing through the axis. F1, my bad, F2 produces a torque because the lever arm is not 0. Okay, now we have this question as well. We have a similar question in the standardized test preparation as well. In that case, of course, you can see that this is the axis of rotation for a bicycle. And here's, you could say, the radius of the wheel, so that'll be the distance. And then the other question that we have, it gives another force at this point here. Let's call it F3. So what is the question? It says two forces, or you can say three forces of equal magnitude act on the wheel as shown in the figure. Which of the forces will produce the greater or the greater torque on the wheel here? Clearly, you can see that for this one, it is F1. Why? Because it is acting at right angle to the axis, or you could say to the distance. There is this force which is at right angle to the distance, which produces the greatest torque. What about this one? You could see that this force is acting at some angle here. This angle is not 90 clearly, so it is less. But what about F3? F3 produces no torque because it is passing through the axis of rotation. So F1 produces a greater torque. This diagram, of course, it is a diagram from a book. It says a cat shown below is pushing on the same door with the same force at the same distance from the axis of rotation, but at different angles, okay? Resulting in different amount of torque, and that is clearly obvious. So we know that, let's say, this is the axis of rotation for each one of these. You can see that, for example, especially you might have seen this one on TV. There are some doors. They have a small openings that allow pet animals, especially cats, for example, to go in and out freely, like whenever they want to. So this is one of them. But if you look at this one here, it says each one of these is basically, or this cat is applying the same force at the same distance all the times. But the only thing that is different is the angle. And we know that torque is equal to F times distance sine theta, yes? As you can see here, this angle is 90 degrees, which we can say at this point we have maximum torque. Okay, but now the second case here, you can see that same distance and force, but the angle is now less than 90. So we can say the torque at B here, it is going to be less than the torque. So this torque, it is, of course, less than the torque than A, let's say. A was bigger. What about this one here at C? You can see that the angle is even smaller than this angle. So we can see that the torque at C, it is going to be the least. So if I, let's say, rearrange these, you could say torque 1, it is maximum greater than torque 2, which is greater than torque 3 here. You can call this one A, you can call this one B, and C as well. And of course, clearly, torque depends on both force and distance. If you increase the force, it's going to be bigger. If you increase the distance or decrease the distance, that affects the torque, and that's it. All right, now we have another question which is also interesting. Says what? Two forces equal in magnitude but opposite in direction act on the same point on an object. Is it possible for there to be a net torque on the object? Explain your answer. That's also a very good thing. Watch this one here. Let's say we have an object. Now, we have two forces of equal magnitude, let's say 10 and 10. But these two forces are acting on the same point at the same distance, you could say, from the axis of rotation. So will there be any net torque, clockwise or counterclockwise? No. Why? Because these two torques are going to cancel the effect of one another. So this beam, you could say, it is not going to rotate, so there will be no torque. So the answer is going to be no, because the two forces acting on the same point, they cancel the effect of one another, so there will be no rotation. Now we have another question, which is this one. Also, this one is interesting question. It says a basketball being pushed by two players during a tip-off. One player exerts an upward force at 15 Newton at a perpendicular distance of 14 centimeters from the axis of rotation. The second player applies a downward force of 14 at a perpendicular distance of 7 centimeters from the axis of rotation. Find the net torque acting on the ball about its center. Now, this point, of course, the good thing about this question is the diagram will be given, because if the diagram is not given, then the situation might change, because it depends on whether or how you draw this, the forces at this point. So, of course, if the diagram is not given, they must give you enough detail so that you know which force is at which side and which direction is it, so that you can make the right drawing or calculation here. So this is what we have. So we have, it says, an upward force. This upward force is 15 at a distance of 14 centimeters. And then there is another downward force at the other side, which is 11 Newton. This one is at 7 centimeters. Okay, so how do you find the net torque? But before we find the net torque, how about we do the directions here? You can see that, for example, this one is going to rotate the basketball in this case, so which is going to be clockwise. Clockwise is negative, right? What about this one? This one is also producing a clockwise torque here. So these are both going to be negative, negative. So in this case, we're just going to add them together. Okay, so we could do them here. We could say the net torque, that is equal to torque 1 plus torque 2. Yes? Now let's just find the value for torque 1 and torque 2 and see how much they would equal to. Torque 1, that is equal to force times distance. No angle, so we don't write angles here. The first force, it is 15 times, remember, the distance that we have, it is 14, so convert that to meter. That is 0.14, and then you will find the answer, which is going to be, once again, these are, we said these are clockwise, so you could say negative. Okay, and then whatever the answer is, which we're going to write it in a second, or we're just going to take a look at it, Newton meter. That is for the first one. What about for the second one here? Say torque 2, again, force 2 times distance here, you could say. All right, so at this point, the second force is 11 times, these are, by the way, clockwise, so negative 11 times 0.07, because convert the 7 centimeter to meter, that would be 0.07. Let's see what are these values are. So the first one is going to be negative 2.1. Here's negative 2.1. The second one is going to be negative, negative 0.77 Newton meter. So how do you find the total now? Negative 2.1 and negative, here's the total, negative 2.7. Or you could just say minus at this point, negative 0.77. So what is the answer? Just going to add these two together. My bad, this is 2.1 right? So it is going to be negative 2.87 Newton meter. You could just write 2.87 clockwise if you want to. Oops. All right, clockwise. If not, by the way, you can round it up to 2.9 as well. That's this easy. Nothing much or no difficulty regarding this one here. All right, that is regarding this one. By the way, we said you just write one of them, either the negative or the clockwise. This negative, it means the clockwise. It is in bracket so that you know what it means here. All right. Let this be the last thing for today. It says, in this figure, remember the one that I told you like earlier? It says, in this figure, three forces acting on the bar have equal magnitude. Which of them, right? Which of them does not produce a torque about the axis which is at the left end of the rod in here? So as you can see here, this is the axis of rotation. We said this one, because it is passing through the axis of rotation, produces no torque. What about this one here? If you extend this one, you can see that even F1, it is passing through the axis of rotation, so this too does not produce any torque, okay? And that is what the question is wanting. It says which one does not produce? That is F2 and F1, which is A at this point here. What about this one here? It says, which of the following statement is correct? Let's do this one too. It says, the further the force from the axis of rotation, the less the torque. That is incorrect. Remember, this is the equation that you have, F times d sine theta. The further, that means the bigger the distance. But the question says the bigger the distance, the less the torque. Is that correct? That is incorrect. So A is incorrect. B says, the closer the force from the axis of rotation, the more the torque. That means if the distance is small, if the closer, the torque will be large. That is also incorrect. Don't forget this, because these two are directly proportional to one another. Here says if the distance is small, the force will be, or the torque will be, my bad. Here's, sorry, that is the torque and the distance here. Okay, so it says if the distance is small, the torque will be large. Is that true? That is not true here. So B is also incorrect. It says the closer the force from the axis of rotation, the easier it is to rotate. No, because when we say the easier, that means the larger the torque, which is also incorrect because the more difficult. What about D? That says the further the force from the axis of rotation, the more the torque. That is correct because these two are directly proportional. So the further the distance, the larger the torque. And this is the correct answer. This question regarding the basketball, this is the same as the one that we just did. So give it a try. This would be the end for this session. I would like you to, perhaps how about, actually let's, let's just say a few more seconds to answer these questions. I thought it was coming the other question actually. So the perpendicular distance, whenever you see the perpendicular distance and it talks about from the axis of rotation, right away, that is the lever arm. Because we said the lever arm is the perpendicular distance. What is the rotational analog of a force? Remember this, we said in grade 11, we had a force which when you apply, it makes an object move forward or backward, or even change direction. But at this point here, when you apply a force at some axis, some distance, let's say, this force causes rotation. So now, of course, we have torque in grade 12. So we can say the analog of force in translation, it is going to be torque in rotation, which is, you could say, the substitute of force is going to be the torque. Okay. So which one is it now? It is going to be B. Okay, what is the rotational analog of a force? It is the torque. 3 says a quantity that measures the ability of a force to rotate. You know that this is the torque, right? 4 says, remember it told you, it says one of the following is equal to the unit of Newton meter. We said it is kilogram meter squared, second squared. You can always do that again just to see whether right or wrong. The SI unit of a torque, it is Newton meter, don't forget. This is the SI unit Newton meter. This will be equivalent to Newton meter. It says which rotational quantity, again, is equivalent to force. That is, again, it is a torque. And that will be the end of this session or this video for today. Inshallah, next time we're going to start with this question right here. And of course, I'll tell you another idea regarding this one that's never been in a Wuzari, for example. What if the question asks you to find the tangent in the string, which is a possible question maybe. Till then, keep practicing and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.